Okay, for this teaching segment, what do we do when we got a UDL? Well, first of all, what is a UDL? UDL stands for Uniform Distributed Load. So if you imagine that we've got our beam, and on the beam we've got, I don't know, let's say 20 kilonewtons, and the beam is 2 meters long. As opposed to the problems that we've been doing before, where we'd have 20 kilonewtons being applied at a particular point, in this case, that 20 kilonewtons is being applied all across the beam. And on a free body, we tend to do it as a shaded section like that. Above it, I would put UDL to tell the reader that that's what I'm dealing with, and I would say how much weight per meter I've got off my UDL. In this particular case, the total weight of the UDL is 20 kilonewtons, so what I need to do is take my 20 kilonewtons and then divide it by the fact that it's spread over 2 meters, and so that gives me 10 kilonewtons per meter. So that's the number that I'm going to write up here. So I'm going to have 10 kilonewtons per meter. Okay, so that all seems fine. So we've got two reaction points, A and B. We've got this distributed load pushing down on these two reaction points. So that's about it, really. So next thing is to work out what the reactions are going to be. Well, because this is nicely distributed, we could all do it by what I call inspection. That is that we can just apply our engineering brain and use logic on the problem. So if overall we've got 20 kilonewtons being applied on A and B, it's going to be uniform distributed. It means that we're going to have 10 kilonewtons pushing down on A and 10 kilonewtons pushing down on B. Well, so that's our solution. How would we do this solution if we were going to try and be a bit more formal and use maths to solve it? Well, what we want to do there is actually use the principle of how we know forces behave on bodies. So a force, if I push a force through the center of mass of the body, it's the same as if I'm pushing against the whole body. So this problem, in terms of how the forces are going to behave, is the same as a problem where we've got a pivot here, a pivot here, we've got a massless beam, and we've got a concentrated load, and the concentrated load is 20 kilonewtons. Okay, so as far as these two pivots here are seeing, these two supports, for them they see no difference between this thing here pushing down on them or a concentrated load with a rigid beam here pushing down on them. To them it's the same. And if I've got this problem, I know how to deal with that. So I've got A, B, it's 1 meter to get to the center of mass of the UDL, 1 meter to get to the center of mass from that point from the UDL, and I would just use my approach of summing up forces in the x direction. Okay, I see that I have no forces in the x direction, so 0 equals 0, doesn't tell me anything. Then I'm going to sum up my forces in the y direction. Right, so I have a reaction point here and a reaction point here, so I'm going to have RA take away 20 plus RB equals 0. Therefore, RA, I'd like you to do a new line here, plus RB equals 20, where we're working in kilonewtons. And the final thing will be to take moments. Take moments at a logical place. Sensible place here is at pivot A. So we're going to go round pivot A in a clockwise sense down there. The distance from here to here is 1 meter. The arrow is pointing downwards, the clockwise symbol is pointing downwards, so that's going to give me 20 times 1. Next one that I've got is this reaction force, which is pointing upwards. That's pointing downwards, so that's going to be a negative moment. So the distance from here to here is 2 meters, so minus 2 RB equals 0. So, well, that's straightforward. 2 RB equals 20. So therefore we've got RB equals 10 kilonewtons. Go back to this equation here. Let's put 10 in there, and then we have RA equals 10. As we would have expected, we didn't really have to do any maths to solve it, but that just takes us through the process of what we'd want to do to solve this problem. Okay, so that's what a UDL is. How we're going to treat the UDL to what we're going to do is convert the UDL into a concentrated load and go back and just solve it like the sort of ways that we were solving previous problems. So that's all we have to do. We'll just do one complicated example and then we'll leave it there. Right, so for my complicated example, I've got a 4 meter long beam, pivot offset here, so we've got 1 meters, 1 meter, and then 2 meters. Right, I'm labeling these up as A, B, C, D. So we've got, this is going to be B, so reaction at RB, a reaction at RD, at position A I'll have 10 kilonewtons going down. I'll put another 10 kilonewtons here, and then across here to represent my UDL I'll do this time a kind of gate looking thing here. Alright, I'll tell you it's a UDL and it's going to be 25 kilonewtons per meter. So how do I solve this problem? Well, the first stage is to convert this problem as if it was just concentrated loads. So we have to, the best thing really is to draw it all out again with concentrated loads. I've got 10 going down there, I'm working in kilonewtons. I've got 10 going down there, working kilonewtons, I know where they are, looking at the diagram above. Here I've got 2 meters worth of this UDL, So to find the total mass, sorry, the total force of the UDL is going to be 2 times 25. So 2 times 25, that's 50. Next thing is to work out where's that going to be. Well, the center of mass for the UDL is going to be 1 meter from that start position. So that will be this location there. So that's 1 meter. So we know that the start location is 1 meter from this pivot B. So we've got 1 meter plus another meter equals 2 meters. So let's put that on our diagram. Okay, so I've got 2 meters to get to that point there. Right, now let's start doing the forces. I'll do the force Fx over here. It's redundant. So sum of the forces in the x direction, and I'm going to get 0 equals 0. Now let's look at something more interesting. Let's sum up the forces in the y direction. So starting here, we're going to have minus 10. This one here, we're going to have plus RB. This one here, we're going to have minus 10. This one here, we're going to have minus 50. This one here, we're going to have plus RD equals 0. Let's do it therefore. Okay, you should do a new line. So unknowns is going to be RB plus RD on the left hand side. The knowns are 10, 20, so it's 70. Okay, now the next thing is to take moments. Where I'm going to take moments, the best place to take moments is the leftmost pivot there. So that would be at RB. So we go around there, and then we'll come up here like a clockwise face, and I'll take a pivot at that point there. Oh, you can almost see my colours. Right, so I'm going to take moments. I'm going to tell you where I'm going to do it. So at B, and I'm going to tell you I'm going clockwise. So first one that we see is that we've got a force going downwards, and this clockwise symbol is going up. So that arrow and that arrow are pointing in opposite directions, so it's a negative moment. So minus 10 times by a distance of 1. Okay, now let's look for the next one. So it's from here to here. In this case, it's going to be plus 10 times by 1, because you can see that my arrow is going downwards and this is going downwards, so they're going in the same direction. Next one that I can see is going to be this one here. That's going downwards and that's going downwards, so that's plus 50 times by 2. And then finally the distance from here to here, well, I have to go back to this diagram. So the distance from here to here is 3 meters, so that would be minus 3 RD equals 0. So therefore I have 3 RD equals, well actually this is quite straightforward, because that and that just kind of cancel one another. And we're going to end up with 100. So therefore RD equals, well, let's get your calculator out. So 100 divided by 3. Right, so press the SD button, is 33.3333. Let's work to 1 decimal place. 3 sig fig. Okay, now let's find the RB using equation 1. So from equation 1 I'm going to have that RB, I'll substitute in my plus 33.3 equals 70. So therefore I have RB equals 70 take away 33.3. Right, so what's that going to be? 70 take away my previous answer equals 36.6 with a recurring symbol, get rid of the recurring symbol. So we've got 36.7, round it up. Kilonewtons. Okay, so we're saying that RB is roughly a little bit more than what we'd expect at RD. Does that seem to make sense? Yes, I suppose it does, and we would have weight pushing down here, weight pushing down here, but we've got a lopsided UDL over to that side. So yeah, that seems to be a sensible answer.